This is a very exciting section for us to be in because you are in third semester calculus. And we've been together for several weeks now. And I believe this is going to be the first time we're going to actually do any calculus. If you think about it, all of chapter 12, we were just getting comfortable working in 3-space. And then when we started with vector functions, we were just defining what they were. We talked a little bit about graphs, we talked a little bit about domains, but there are 3 main topics in calculus: limits, derivatives, and integrals, and we haven't done any of that. Well, that's going to change. So we're ready to start doing some calculus with this new sort of function. So we're going to be looking at limits of vector functions. So I'd write it something like this: the limit as t goes to a of r of t equals L. So we're used to seeing things like the limit as x goes to a number of f of x. So we're saying our input is approaching some number. The output r of t would be approaching some vector. Okay. So the limit is itself going to be a vector. Now what this means is exactly what we're used to. It means as t approaches a, the vector r of t approaches the vector L. Now what exactly does that mean? Well, let's just suppose that r of t was a vector function in 2-space. Looked something like so. So I've drawn a vector function with an orientation here. Okay. Now, of course, when I graph the vector function, I'm just graphing these points, but I'm interpreting these points as the tips of vectors. So I could, particularly if I want to talk about individual points on the curve, I could choose to draw them as the position vector that points to that location. Now, let's suppose that our limit L is this vector right here. So what does it mean for r of t to be getting close to L? Well, I could think of it in terms of points, because what I'm graphing is the tips of these. So every point on this curve is the tip of a position vector. Okay. And as I know, as t is increasing, I'm coming along this curve. So this would be saying as t gets closer and closer to a, and we could be approaching from either direction. This is a 2-sided limit. So if t is increasing, I'd be coming this way. If t is decreasing to get closer to a, I'd be going against the orientation. But as t is getting closer to a, the point on the curve would be getting closer and closer to the point corresponding to the tip of L when it's drawn in standard position. I could also interpret this by thinking of the outputs as actual vectors. Okay. Notice this vector and this vector. Well, they both have a magnitude and a direction, and right now they're both a little bit different. But if, as t gets closer to a, the tip of my vector is getting closer and closer to this point right here, then the position vector is approaching the length of this and the direction of this. Okay, so we sort of have a sense of what it means for a point to get close to a point, or a vector to get close to a vector. Of course, if we're a vector getting close to a vector means that both the magnitude and direction are getting close to each other. And what that means is as I'm drawing things in standard position, this is getting close to just overlapping with this. Okay, now how do I go about evaluating things? Well, if a point is getting close to this point, we're in 2-space, 2 things have to be true. The x values of those points have to be getting close together, and the y values of those points have to be getting close together. And if I think of them as vectors instead of points, same thing. In order for 2 vectors in 2-space to be close, they would have to have a close x value and a close y value. In 3-space, I just have to throw in the z value as well. Okay. So I can say that the limit as t approaches a of x of t, y of t, this would be an arbitrary vector in 2-space, is simply the limit as t approaches a of x of t, comma, the limit as t approaches a of y of t. Okay. In other words, we evaluate limits component-wise. So in order for this one vector limit to exist, these 2 real valued limits of each component function would have to exist. If either one of the component functions, the limit doesn't exist, I don't get both, so I can't take the limit of the vector function. Okay. And, of course, if we are in 3 space, same thing is going to be true. I'm still going to evaluate my limit component-wise. I'm just going to have a third component. So the limit as t approaches a of x of t, y of t, z of t is, one vector limit in this case is 3 real valued limits. Limit as t goes to a of x of t, limit as t goes to a of y of t, limit as t goes to a of z of t. Okay, so let's just take a look at an example. Let's suppose I wanted to take the limit as t goes to 0 of cosine of t, sine t over t, let's do one more. We'll do t cubed over t squared. Okay, now you'll notice this function is not defined at 0 because the y and the z components aren't defined at 0. That doesn't mean, though, that we can't take the limits. Okay, so this would simply be the limit as t goes to 0 of cosine of t, the limit as t goes to 0 of sine t over t, and then the limit as t goes to 0 of t cubed over t squared. Now, this first limit I would evaluate by simply plugging in 0. Cosine of 0 is going to give me 1. These next 2 limits I can't evaluate by plugging in 0, but I've got a couple of options. I might remember that this limit is 1. If I just remember that, I can say, oh, it's 1. If I don't remember that, I could work it out off to the side. Limit as t goes to 0 of sine t over t. Notice the top is going to 0 and so is the bottom. So I could L'Hopital it. So I could say this is the limit as t goes to 0 of cosine of t over 1, which is just 1. Beauteous. Okay. This one here, I could also, if I really wanted to, L'Hopital it, but I think it's easiest to say I can just reduce that. So the limit as t goes to 0 of t cubed over t squared becomes the limit as t goes to 0 of t, which is just 0. Okay. So I may be using different limit techniques in the different components, but as long as I can legitimately evaluate each of those limits, we're in good shape. Okay. I do want to just give you one word of caution, however. I want to compare 2 limits that at first might look very similar, but are actually quite different. Let's look at the limit as t goes to 0 of 1 over t minus 1 over t. Okay. And let's look at the limit as t goes to 0 of 1 over ti minus 1 over tj. Okay. Now this is a real valued function. This is a vector function. All I've done is said this had 2 terms, and I've made those terms the component functions that I have right here. Okay. Now, if I wanted to evaluate this real function, often when I have multiple terms, I can take the limit of each term and subtract the results. Here I can't do that because the limit of 1 over t doesn't exist. Okay. If I look at 1 over t, I can't even say it's infinity or negative infinity because 1 over t goes off to negative infinity if I approach from the left, but off to positive infinity if I approach from the right. So I can't evaluate each of those individually, but I don't have to. Because I'm saying, let's take the limit of this whole thing. I could subtract those. And this becomes the limit as t goes to 0 of just 0, which is 0. Because this is 0 except when t is 0. It is undefined if t is 0, but everywhere else it's 0. So if I were to graph that real valued function, where this is my t-axis, it would be a very boring function. It would just be the t-axis with a hole in it at 0 because it's undefined. Okay. Now here, I can't do that. These are i's, these are j's. Nothing's going to cancel out. I can't combine these. It's almost easier to see if I've written it in bracket form like so. I'm supposed to take the limit of this function and the limit of this function separately. Just because I wrote it in terms of i's and j's in subtraction doesn't mean I can combine these. These aren't like terms. These are i's, these are j's. Nothing cancels out. This limit does not exist. DNE is my abbreviation for does not exist. Okay, so do be very careful. You do have to be able to take each limit individually in order for the limit of the vector function to exist.